Hello and welcome to the Introduction to Side Channel Power Analysis training module. So this is part of the online training available at chipwhisperer.io, and I'm going to take you through how side channel power analysis attacks work on hardware devices, what they are, what sort of things might be vulnerable to them. So I developed the open source toolchain called ChipWhisperer, which is a full software and hardware combination, and you can use them apart from each other, so you can use the software without needing the specific hardware and stuff like that. So it's a really complete open source project that I spent a lot of time developing, and I think it works quite well, but I'll show it throughout this presentation as well. So to begin with, you have to ask yourself, what does encryption do for us, and what's kind of the point of encryption in our day-to-day life? So a classic encryption is that you have, two people that might need to communicate. So you might have something like a ship out at sea, and the Navy wants to send a message to it. Now they can use radio for that, but the problem is that if they send that radio signal, anyone else, is able to receive it as well. So they send this big magic radio beam over, and anyone else can intercept that and read the message. So to solve the problem, they would use encrypted ciphers. So this means that rather than sending in, attack at dawn, they send some garbled-looking text that the ship is able to decrypt to figure out what the message would be. So the most famous system is probably the Enigma machine. So this was used by Germans primarily, and actually others use them as well, but they're most well known for the use in various divisions of the German military. And how this would work is if you had a message, there's a number of settings at the top and bottom that you don't see in this photo. And the sender and receiver would have to make sure they're using the same setup. This would mean then that if you type your message in, you hit the A key, one of these lights will then light up, maybe the F key. Then you hit the T key, and then a different lights up, the H key. So this is telling you what message to send over the air. The key thing is, if you hit the T key twice, because attack has two T's in it, it's not just simply mapping the T to some other letter. It's using a cipher, and that means that the next time T is mapping to W, so it's using a more advanced cipher than just a simple substitution. And so this is, a really basic example where you might use encryption just to stop someone else from reading your secret message. Of course, this extends to a whole range of other services. Encryption can be used, for example, when you're putting your banking information in online. This is how you are, guaranteed more or less that the communication at least is secure. Maybe there's other security flaws, but at least no one can read your credit card number directly off the internet traffic. Encryption's also been critical for lots of stuff like cloud computing. So, you have your magical cloud here with some servers in it that are doing something, and you might not even know where these are located. Your business, even though it doesn't know where these servers are located, could use them to store data because your business, their physical building with their nice little door and window, they can encrypt the data in-house, so they're encrypting it, and this data is then transmitted and stored in the cloud. If someone takes those cloud servers or breaks into them or anything, it doesn't really matter because all your data will be effectively meaningless, assuming the encryption has been done correctly, and will just look like random data. Only you are able to access that data, so when you download it, you're able to, convert it back to the original whatever it was you were doing, your amazing report or something like that. So encryption, people might first think of it as just really simple. Okay, it protects some information, but it's fundamentally changed a lot of, history and continues to change how we interact with the world today. The ability to use this type of cloud technology, the ability of the internet to connect everywhere is driven largely by encryption, allowing us to protect data that otherwise people could easily see. So there's a few phrases you're going to hear once we start talking about encryption, and so you should be a little bit familiar with them. The first is when we're talking about an encryption algorithm, we could draw, a little box that does our magical thing. And this is what we're using to hide our data. So encryption here. We put plain text into the encryption. So the plain text is, our message that we want to be able to transmit freely. So if I say attack at dawn, or how about just attack because I'm running out of space, it goes into the encryption engine and it's translated, and that's our plain text, into the ciphertext. And so, this will just be some random collection of letters, and we could give it the same number or not, depending on who knows what our algorithm is. So we end up with something like that. So we have plain text, we have ciphertext. The critical thing with the encryption is that there's a secret key, and this secret key is really fundamental to the ability of the system to work. So the secret key is generally what we're calling what the receiver would need to be able to decrypt that message. So the secret key, obviously, there's a lot of tricky business around making sure the receiver has that secret key and not an attacker. If an attacker gets that secret key, all is lost, is basically the assumption we're making about the encryption system. One really important thing here is that we don't want to have secrets inside the design of the algorithm, so we have no secrets here. And that's to say that if someone knows what algorithm I'm using and how it works, it shouldn't help them in any way, decrypt my message. Everything should be related to that secret key, should have 100% of the secrets in it. This is to say that, for example, if someone captured one of these machines, and why you wouldn't want this is if you capture this Enigma machine, you don't want it to mean that now they can easily decrypt all of the messages. So when we talk about strong cryptography, what we're typically meaning is that it's cryptography that's difficult to break, and it's difficult to break even if an attacker knows everything about how this algorithm works and what it is. As long as they don't know this secret key down at the bottom here, then we're safe. There's two main types of encryption we'll run across too, so symmetric and asymmetric. So symmetric crypto uses the same key for both sides of the conversation. So I'm now going to revert to the classic Alice and Bob that you'll see as these fictional characters. So assume we have Alice, and she's going to send a message, an enciphered message over to Bob, and we'll have Bob over here, and I'll use them to explain the difference between, symmetric and asymmetric crypto. So assume Alice gets her letter here and now wants to send it to Bob in a secure manner. To do that, what she might do is use a encryption machine, and we'll just draw a big old widget here. So this is the encryption machine. So the letter goes in this machine and is sent to Bob. At the same time, the other thing this machine needs is that secret key. So I mentioned there's this, secret key that really defines how everything works. So we'll make this in red here. So this is the secret key. And Bob, on the other side, he has the inverse of this. He has a decryption machine. So let's make that so it goes in the top. And so this is his decryption machine. Now this machine needs that same secret key. So they had to agree ahead of time what that key was. Maybe they exchanged it when they were on holiday at some point. And that key they can reuse a number of times because, exchanging that one key was difficult. And it doesn't matter if someone intercepts the message, they'll never be able to figure out that key. So that's symmetric crypto. And, this shoots off into his waist. So the secret key is in the same spot for both of these. And it's the same key is the critical thing. So it's the same key with symmetric crypto. Asymmetric crypto is a little bit different and potentially a little more, useful, because the one issue with that is the distribution of that key is very difficult. And as soon as an attacker gets it, it's useless to us. So in practice, you have to change the key quite often because you don't know when an attacker might have gotten it. So you want to make sure even if they do acquire it, they don't get a year's worth of messages. They get a day or an hour or a second's worth of messages. So asymmetric crypto is a different way to exchange messages. It's not as computationally efficient, so symmetric crypto is much faster. And in most systems actually use a combination of these. And that's because they'll use asymmetric crypto to distribute the key and then symmetric crypto to distribute messages. Anyway, back to our story here. So with asymmetric crypto, Bob actually publishes two keys. He has two keys. He has a public key that he just puts on for the world to know. And he has a private key that he'll hold in his hand because it's very important no one finds out this private key. So there's two keys rather than with symmetric crypto, there was just one and it was always the same. So again, back to symmetric, this is the same key. With asymmetric, it's different keys. So when Alice wants to encrypt a message, she again uses her magical encryption machine here. But she doesn't have to, use this key that's only known between her and Bob or something like that. In fact, what she's able to do is she just takes Bob's public key and plugs it into the machine. So this public key she can download, from Bob's web server, or Bob can freely send her. The critical thing with it is that this key is no good for decryption. So you can't use it to decrypt the message. You can only use it to encrypt the message in this example. So again, she puts it through the machine and is going to send it to Bob. Bob has his, decryption machine here. But what he plugs into it is his private key. And this generates the original message out. So he goes ahead, takes his private key and moves it over here, plugs it into the machine, and he gets this message out. Anyone else trying to use the public key isn't able to decrypt the message. They can just send him messages. So you can see this is a nicer system because it doesn't rely on this, magical out-of-band exchange of the keys here. In fact, what we can do is use asymmetric to do this magical exchange of the keys, and then use symmetric crypto for a little bit, and then just change our keys ever so often. All right, so those are the two types of encryption. And again, with all of them, we have this idea of the plain text is the input or the information in a useful form. Ciphertext is once it's been encrypted, and the secret key is what is mapping the plain text and ciphertext in some sort of form, in combination with the algorithm. So where did these algorithms come from? Obviously, it's very difficult to correctly produce one. So there are some that have spun out of industry. So Data Encryption Standard, DES, was originally, I believe, an IBM research group project. But all of the good standards have been subject to all sorts of scrutiny. And this is to say they're widely published. They're not secret. The algorithm itself should never be secret. So, in the case of DES, even though it was developed possibly by a company, it's published for academics to do any sort of research they want. So you have this ridiculous stock photo of an academic. You can give him a name here. Hi, I'm John. And they can try to find weaknesses in the system. Algorithms also may come from the academic community. So, they may be theoretically published for people to find weaknesses in them and then used by industry. But it's very much a research-heavy focus. And this is because there's a lot of attacks that are continuously coming out. And it's very critical that algorithms remain mathematically secure as sort of the foundation for everything. If there's any sort of weakness in them, theoretical weakness, that could basically ruin any future use of them. So once we have, a an encryption algorithm, it's typically published in some form. So this is FIPS publication 197, which is AES, the Advanced Encryption Standard. So, this document, it goes through quite a bit. So it has some of the theory. It's not describing necessarily where all the security comes from. So that's typically more discussed in academic publications. But, it talks about here's how you implement it, here's how it works. And it'll have some pseudocode of, what the algorithm looks like. So from this, you can then hopefully go to a software implementation of it. So some sort of C code or something like that. So this example here is a C implementation of part of AES. So it's using C variables and stuff like that to do these various functions. In this case, it's actually implementing sort of this section here is being implemented as part of this. And, you can test this code. You can validate this code is equal to this algorithm here. This is something we can do. So we could verify, it does perform correctly. We could go through and verify things like, is there buffer overflows where it's being used? Can we close those? So up until this point, we still assume everything is secure. So until this point, everything is totally secure. And that's a really critical difference between the type of attacks I'm going to talk about here, is that they aren't necessarily mistakes that are being made. They're in fact very fundamental in how systems are implemented. So let's look at where we might use encryption and how that gets implemented in real life. So take a module. So this is a little circuit board, and you can see we have a micro here, so a microcontroller. And it's capable of running code to do something. So let's say we have, maybe we have a vineyard, and we have a little box here, and we control when it gets watered. So we'll draw a little water coming out of it. And the other vineyard owners are actually kind of jerks, and they're always trying to ruin us. And we wanted to have a wireless system, but we want to make sure the other vineyard owners don't, send us messages that drown out or disable our system or something like that. There's all these wireless messages incoming. So we're going to use encryption. And what the encryption will do is it'll allow us to validate, when we send it a message, to validate that, hey, this message actually came from us. So, turn on the water for 30 seconds or something like that. So on the circuit board, maybe there's a separate radio module, and it just receives these messages and sends them onward. It doesn't know if they're valid or an attacker's. Inside the system, what it will do is it'll decrypt. So we'll have a decryption algorithm. So we'll select a decryption algorithm, and it uses a secret key. So we preset up a secret key inside this device. We programmed it in, and then only we know it. So even if an attacker sends messages, it's never going to work. So it'll decrypt the received messages. It could do some further validation of them. So you look to make sure it was decrypted properly and that whoever sent it knows the secret key. And if so, maybe it sends a signal out somewhere to switch on the water. So this is a fairly typical embedded hardware task that might use encryption. And if we look inside that IC here, so this is actually a similar microcontroller, but not that exact IC. But there's all sorts of stuff. So we can see at the side here, these are the pins, going off to the inputs and outputs to give you an idea for the scale. And if we look way in, so you zoom in, I don't know if this is around here somewhere, it looks like maybe. This guy here. At some point or another, you're going to start seeing these metal layers. So you can sort of make out, various foils, and some of these will actually be a data bus. So when we go to, do something in the code, so for example, right here we have an increment, or we have an XOR or anything like that. What's going to happen is that somewhere in the chip, and I don't know exactly where it is in this device, there's going to be a bunch of registers that store, for example, the value of that counter. There's going to be something like an ALU. Some section of this is going to be the ALU, and it's going to send data back and forth over the data bus. So this physically means, it's going to take the data that was something like, say, 0, 1, 1, if it was binary 3, send it to the ALU, and the ALU will send back, 1, 0, 0, because it incremented by 1. And all this will go over, wherever the data buses are in the line. So if it's an 8-bit microcontroller, it'll have an 8-bit data bus. So somewhere on this chip, there's these physical wires representing the data flowing around. And we kind of have to go back to high school physics here, so ignore the ridiculous high school stock footage, but you get the idea. And what we have is inside the chip, we have these various data buses. So these are the wires, and you can just imagine them as pieces of metal. And there's going to be another somewhere, like a ground, either ground plane or the substrate, something like that connected to ground. So I'll just draw this. If we had a side view or a top view here, it would look like this was over everything. This is top view. And if we did a side view, what you might see is it's basically just two parallel plates. One of them is connected to ground, and this guy gets a voltage put on it. So if we send a logical 1, we might put plus 5 volts, and if we send a 0, we put 0 volts. So this wire gets connected to 5 volts or 0 volts. Now, this setup here, where we have two wires separated by some distance, is really just like a capacitor. So, this is the initial capacitor they discovered was just pieces of foil separated by a dielectric, which was the glass jar. And they discovered you can store electricity on this. You can store charge. So you can put electrons onto this device. And in doing this, you're physically moving electrons, depending which flow you're using. You're physically moving electrons on or off this electrode. So probably that way because the outside's negative. And this actually involves work being done. So this is interesting because it starts to mean that when you charge or discharge a capacitor, it actually takes a small amount of work. And the really interesting thing is that, yes, you might know capacitors as those things that blow up on your motherboard or something like that. But these tiny lines are actually functioning as very small capacitors, even though they weren't designed to function as such. Now, the interesting thing is that in order to move charge on or off a capacitor, so if we had the ground and, we had a positive side here, if we want to charge this up, so if we want to say, okay, we're going to put plus 5 volts on here, it takes a very, very small amount of energy, physical energy, because we're actually moving charges around. Likewise, if we take that and then we say, actually, we want to have 0 volts on this, so we'll short that together. This is equivalent to, very small amount of energy changes that you can again measure. And it might seem like a small amount, but as we'll see, it's enough that you can measure it with fairly simple equipment. So this might not, so what I've explained so far is that, this change in voltage of the capacitor we can measure, but why do we care for our digital devices? Well, if you consider these digital devices, they have data buses. So this is like a 4-bit data bus here. And what we might have is, let's use our earlier example, where we're going to write 0, let's go with 0, 1, 1, 0 on the data bus. So on the physical device, 0, 0 volts, 1 volt, 1 volt, 0 volts. On the physical device, it's then going to increment this number. Now it increments it using a clock, so I'll draw this dotted line to show when it'll change state. And we'll have a few of these, so let's add a few more. There we go. So at this point here, what's going to happen is it's going to increment this number, and this number will become 0, 1, 1, 1. And so we can say, okay, well, this guy will go from 0 to 1. This guy will stay 1. This guy will stay 1. This guy will stay 0. And likewise, we can do the same thing once more. So we can say, okay, well, the next time it increments, it'll become 1, 0, 0, 0. And so this will go to 0. This will go to 0, to 0, to 1. So all I'm showing here is the waveform of the device on the data bus. Now, when the system is actually physically changing these lines, what you have to remember is, we have these data bus lines. So there's actually 4 of them. I'm just going to show one. So this, for example, is that data bus there. How it does this is it uses electronic switches. They're called FET, so this is where the name MOSFET comes from. And in the systems. Okay, there we go. Ground plus 5 volt. Sorry, so there's these electronic switches that are basically FETs. And as I said, the full name of them, they'll be called MOSFETs. And when you see chips referred to as semiconductors, or CMOS, sorry, part of this stands for complementary metal oxide semiconductor, because it has these 2 pairs of FETs, one sort of the opposite of the other, and it's able to switch the voltage on this bus. So in this case, what we're doing is, let's say we were at 0 volt. So let's say right here, we would have the ground one closed because we're going to put 0 volts on this system. And so this will put 0 volts here. Eventually, when it becomes time to switch it to 1, we're going to open that switch and close the top switch. So we close this switch, open this switch, and this will put plus 5 volts. Now, as discussed before, this is actually just like charging and discharging a capacitor. So this is causing very small power spikes on the various rails. And so we could look at, for example, if this was the plus 5 volt rail, I could say right here, there's some baseline. There's actually going to be a little bit of a spike because of this one line that changed. Over here, we'll have the same thing. We'd have a little bit of a spike. In the plus 5 volt rail, there's only one line that went from 0 to 1, so there's just a little spike here. If we looked in the negative, the ground rail, we'd actually see the opposite because 3 lines went to 0, so there'd be a larger spike in the negative rail. And the same thing over, at this point, well, we don't have any future. We don't know what the next state is here. So we don't know what the system would look like. But let's just say it stayed the same. So let's say these didn't change. What we'd see is there'd be no spike because there's no lines changing state. So this is very fundamentally, when we talk about differential power analysis or a side channel power analysis, is we're looking at the differences, these very minute differences in the system, in the power rail of the system. And in particular, the summary so far is the power spikes we see, the size of those spikes is equivalent to the number of bits changing on the data bus. So if I just sort of hack in another change here, let's say at this point, what we did is it now goes to FF. So if they all went to 1, we would actually see a spike that's 3 times larger. Because 3 of those lines are changing to 1. And in real life, you do see a moderately linear fit. And we will experiment with that later when we get into real hardware. So this is part of that experiments are part of the full ChipWhisperer.io training. So the power is equivalent to the number of bits changing on the data bus. Now, there's one extra sort of caveat here. When we go to look at microcontrollers, they do a slightly different thing, and that is that, we had this state where if you were all zeros with the previous system, and you went to all ones, this would be the worst case. This would be the largest power spike. It also means that, this requires the chip to deliver the most power to all of the bus drivers. And it's also, every time these switch, they're always going all the way from 0 volts to 5 volts. But they're sometimes not. Sometimes they're staying at 5 volts. But you have to design for this worst case switching here. You don't care that often it might not be or often it's better, because you need to make sure the chip, when it switches from 0 to 5 volts, is able to do that fast enough to meet your clock speed requirements. What's sort of a better idea, rather than always designing for the worst case, is let's make the worst case a little better. So what these chips do is they actually start at a pre-charge, and this is halfway between either of the extremes. So before they know what the final state is, they go into this pre-charge. And what you can see now is the worst case is half the swings required. It also means, the power consumption, when they all switch, they're not all switching as far either. So there's a lot of advantage of this from a design perspective. But what does it mean for us as attackers? Let's say we had the same thing, 0, 1, 1, 0. What's going to happen now is the microcontroller at the clock cycle, so let's draw our clock cycle in here, is now going to take those lines to the final state. So in reality, it will, it may want them to be valid slightly before that clock cycle, but we don't really care for our purposes. So it uses that data, and then it puts the lines back to the pre-charge state in anticipation of the next clock cycle. So we put them back to pre-charge, and we draw where our next clock cycle will be. So again, we have this dotted blue line here. And once again, we'll go to, 1, 1, 1, or 0, 1, 1, 1. And once again, it goes to the final state and then back to pre-charge. Final state, back to pre-charge. Final state, back to pre-charge. Final state, back to pre-charge. And it just does this on every clock cycle. Now, the really interesting thing as an attacker using this information is that, so if we look at the power, once again, on the positive, so this is the power, on, say, the positive rail, at this clock cycle here, you'll notice there's 1, 2 transitions that go from that pre-charge state to high. So this means it's actually going to, charge this capacitor, 2 of these effective bus line capacitances. So we'll actually see a spike that's, 2 units large. Of course, the numerical size of this spike, if you could compare the 2 devices, wouldn't be as large because the swing isn't as high. That's the whole point. But we're just talking in units of, what's the baseline of being just one line being set high. In this case, where there's 3 data buses set high, you can see there's 3 transitions from the intermediate pre-charge state to the final high state. So now we have a situation where the device, the power analysis, the differential power analysis or side channel power analysis attack is giving us some sort of measurement related to the number of ones on the data bus. So this is kind of even better data because for every clock cycle, we can figure out something about the data being transferred. So now we have the situation where we get this power equivalent to the number of bits set to 1 on the data bus. So this assumes we're looking at the positive power rail. You can do it on the negative and get number of bits set to 0, or you can do stuff like, if you look at when it actually goes from the this state to the pre-charge, you might get the opposite polarity spike. So the specifics of, if you end up with number of ones, number of zeros, what the sign is, has a lot of variables, but the really critical thing is that we have an equivalence between the number of bits set to 1 and a power measurement. So using this will completely break AES and other encryption algorithms. But how do you exploit this? So I've claimed you can, and this is what the whole field is about. How does this actually work? This is where it starts to get interesting. So let's go back to our, this real simple hardware device. Let's give it a slightly different encryption algorithm. So let's say we take our input data. This is, the one we're validating. We take a byte of input data, and all we do is we XOR it with a byte of unknown data. This byte of unknown data then goes through a lookup table. And this lookup table is basically just changing the value. So if the number was 2, it changes it, to 47. If the number was 61, changes it to 1, something like that. So it's just doing this various substitution of the values. And we know what the values in that lookup table are. And then it actually just goes further on in the chip. We don't even have access to what the data is, but we don't care. That's the interesting thing, is we're going to be able to break this by simply sending it random data. So we'll send data to the device. Send data to the device here. And we're going to measure the power it consumes when it's processing. So we want to exploit this piece of information here. So we know we need to know the power used by the device in a very precise manner. We know how the device kind of works, like we have an idea. We can send it data, so we roughly know when it's doing encryption and decryption, but we can fine-tune that further with the attack. Now, how do you figure out what the power usage was? So this is where a bit of engineering and investigation is needed. You can do stuff like, for example, there may be numbers in the chip that actually give me the device ID, and I can just go look up a data sheet and see what the power pins are of interest. I may just assume, okay, these capacitors here are likely decoupling capacitors, so I can probably figure out which of these are power rails and not. So maybe that guy's a power rail and probably this guy, stuff like that. So using the circuit board, I can kind of figure out what the power pins are. Now, I can do some various techniques. I can lift one of these pins up. If I lift one of these pins, what it will allow me to do is actually physically insert a resistor. So this is all stuff I'll talk about in a later training module about how you physically do these attacks. Another option is you can actually put a probe, a magnetic field or H-field probe, just right over the chip. The changing current generates this magnetic field that can be picked up, and you just do the attack in the same way. So that's one of another way to do it. There's a number of different techniques, but it is quite easy to get these measurements when you have access to a physical device like this. So to run the attack, all I'm going to do is use an oscilloscope to measure whatever system, be it magnetic probe or the physical shunt I decided. And I'm going to have that scope download the data to a computer. I'm also going to have the computer be able to send messages to this device I'm attacking. And what I'm going to have the computer do is send a message to the device and at the same time record the power measurement. So, it's going to send something like C7 and at the same time record what the power measurement was. And then it's going to pick a different number, and it's just picking these out of thin air. And then record the power measurement when the device is going. So this will give us the pieces of information we need. It'll give us the input data while the device is running and a measurement of the power consumption in a very fine-grained manner. So here's a table of what I might get after I've done this. I have the input data here, and I have the resulting power measurements here. So how do we use this to actually do the attack? So this is where we have to start to have a bit of a model of how the device works. So this is just me saying, I know, back here, I know it's doing an XOR, I don't know with what, and I know it's doing a lookup table. So in this case, what I say is, okay, I have a model. I know it's doing an XOR. with some unknown value, and it's a big question mark what that value is. It's then passing it through actually this lookup table right here, and then it goes further on in the chip. And I'm going to assume that, you know, when it's doing it, this is a data bus that it's passing data between. And same thing here. This is a data bus that it's then passing data onward again. So we're going to use this assumption that the number of ones on this data bus here and here is going to be related. So ones on bus is related to a power consumption measurement. And this is something we just assume is true for this particular device. So some of the attacks require a lot of experimentation to figure this out. But this is the type of thing we're doing. So we still, you know, we haven't looked at all about what this secret is. And what the attack will be is that I could guess what the value of that byte might be. So I don't know what the byte is, but let's pretend I did. Let's pretend I said that key byte is 00. What I'm going to do is say, well, if the key byte was 00, I inputted C7, I XOR these together, I end up with C7. I know what that lookup table was, so if I put in C7 to the lookup table, so we go down here to C, and we go across until 7, you can see that the output of C7 would give us C6, so the hypothetical output is C6. Finally, C6, we could convert from hex to a binary and see that this would be equal to 1 1 0 0 and then 6 0 1 1 0. So how many ones are in this number? We just simply count them up. We say, well, 1 2 3 4. So there's 4 ones. I could do the same thing. I could basically go down this list and do the same thing. So for example, 2C XOR with 0 0 gives me 2C. Go to my lookup table again, 2, and we go across to C here. 2C will have an output of hex 71, and we can convert to binary again. So that'll be 0 1 1 1 0 0 0 1. So there's 4 ones here. Hex 89, same thing. So we had 89 input, XOR with 0 gives us 89. We use our lookup table, 8, oops, too far. 8 9 here would be A7. And again, we can say, okay, well, this should be 1 0 1 0 0 1 1 1. So 3 4 5. So we have 5 ones. Same thing with an input of 0 1. Give us 7C. So we can do the same thing. All we're doing is converting from hex to binary. So 0 1 1 1 1 1 0 0. So this gives us 3 4 5 5 ones. And the final one here, D2. So D2 XOR with 0 0 is going to be D2. And you can sort of ignore the colors change throughout, but I'm not using this consistently, sorry. So D2, if we go along D to 2, is B5. So 1 0 1 1 0 1 0 1. And again, we can just count the number of ones. So we go 1 2 3 4 1 2 3 4 5. 5. So all we've done is we've run a hypothetical attack and figured out how many ones we would have had if that key was correct. And we don't know if the key was correct. And we're actually just going to do that for every possibility of that byte. So we can do the same thing for hex 0 times 0 1, 0 times 0 2, 0 times 0 3, 4, 5, blah, 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 up to, say, 3D, and then we'll just keep going. This was just an intermediate value I picked, to show you we're doing the same thing. We're taking, and we'd keep going, a bunch more tests until the final value of hex FF. So for every hypothetical key value, we're generating what the hypothetical number of ones in the output would be. Now, the key thing to remember is we're saying this is related to the power consumption at some point in time. At the point in time where, this value goes over the data bus. So at T, and I could say TA for T attack. So at one point in time, and we don't actually know the specific point in time yet. So the final thing we need to do as part of this attack is figure out which of these is right. So we have a bunch of guesses, and only one of them is going to be supported by the data. And we'll use correlation to look for this. So what we're going to look for is we're going to say, is there a point in time where the number of ones is in fact related to power consumption at some specific time? So now we're going to ask the question. We have this assumption that one of these will be, and we're going to say, where is that true? So correlation, just to refresh your memory, is solely looking for a linear relationship. So this is X and Y correlation numbers. So we can see if there's a perfect linear relationship. I increase X by 1, Y increases by 1. We have this perfectly linear correlation. We have a correlation factor of 1.0. Note that correlation is only looking if there is a linear relationship, not what is the scale of that relationship. So you'll see all of these are also giving you a correlation of 1. Even though the slope is different, but you can't tell that. And this is where, when we do this attack, we don't actually care what how we did the power measurement or the absolute units, because all we're looking for is linear relationships. If we don't have a good linear relationship, so if there's a lot of noise or something like that, we won't get very high correlation numbers. And if there's no relationship, if it's just random, then we would expect a correlation of 0. And when we do the attack, this is one of the first questions people will ask is, well, how do you know at what point in time is this TA? And the answer is you don't care, because other points in time should give you very low correlation because the chip is doing other stuff at this point in time. So there shouldn't be a strong relationship between power consumption and what you think the data on the data bus is. So going back to our attack, we have our power consumption measurements, if you remember. So this was, the measurement 0, 1, 2, 3, 4, 5. And now we have our guesses. So this would have started at 0, 0, and it's just the guess of number of bits set to 1. Bits set to 1, which will also be called the Hamming weight. So we have the number of bits set to 1. We have these power measurements. And we're just going to check for this correlation. And we're just going to check at every point in time. So you can see, for example, I could pick this point in time. I took some samples here. And I could pick another point in time. I took some samples here. I'm just going to put some dots. And let's erase these numbers so they don't confuse you. And we could ask the question, okay, first let's look at when it's FF here. And we're going to see, does it appear like there's a similar relationship between how these numbers change and how the numeric value of these points are changing? So you could see, for example, looking between these first three, we have 3, 4, 4. So what we would expect in the numeric value of the points is they're all fairly similar. So we can see the value, the height here and this height is pretty similar. It's close. Between 3 and 4 is maybe difficult, but the next point is way lower, and we were expecting to see about the same value. Okay, so we can keep going. This next one, that looks sort of reasonable. It's a tiny bit lower than before, and we expected it to be about the same numeric value as the first point. The next point we expect to see to be quite a bit larger, so it's a little larger. and the final point should be a little smaller, but that's kind of wrong because it's even larger. So this would give us, maybe there's a bit of a correlation peak, but not a really strong correlation number. You could also look, so if I pick another random point in time like here, you'll see there's almost no correlation because, we have a high number and then actually a really low, it's like a negative number here, but we didn't expect to see that big of a drop. And then there's like a 0 number and then a negative number. So there's no correlation there. It just visually sort of randomly saying that. But hopefully you can see we're looking for some sort of relationship between what's the number of one set and what's the power measurement. So in this case, when it's equal to 3D, we can go through and do that same trick with the points. So I could say like, well, when it's 4, so there's a certain size point, peak, oh, there's a similar size peak, oh, and then there's a much smaller peak, maybe half the size, and then there's a similar size peak to, I'm just mapping here, a similar size peak to the first ones, and then there's a much larger peak, and then an even larger peak. And so this matches, we have a much larger peak and an even larger peak. So the correlation analysis will actually answer that question. It will give us a very specific numeric result saying what is the correlation at this point, this specific point in time, right here. What's it here? What's it here? And it gives us a number. So it may say, well, here it's 0.9, here it's 0.2, here it's 0.1, here it's 0.3. And we can do that for every guess. And whatever guess gives us the best results at that particular point in time now says, this is one most likely value. So this is the most likely key. And 2, it's most likely at this point in time. So we don't even need to know when exactly the encryption was happening. The algorithm will figure it out, and we'll see that when we actually do a quick attack on AES. So AES, or Advanced Encryption Standard, the nice thing about applying it to AES is what we'll see is that AES itself, at the input, it has a similar functions to the one we just attacked. So it has, this is a key byte, this is a plain text input. It XORs them together, passes it through that S box, and then does some other stuff with it. So what we're going to do with AES is we're just going to attack this point in time after it's done the S box and when it's moving that data onto other sections in the algorithm. And what's really nice is that, so when we look at how difficult it would be to attack AES, so the AES key space size is like 2 to the 128. So it's, it's this huge key space. So it would take, to give you an idea, this 3 point, the size of the key space, the number of possible AES keys is this number here, 3.403 times 10 to the power 38. What that looks like. So if you could try 10 billion keys per second as a test to, try every possible key, you're still looking at like 1 billion trillion years. So even if you find the hit halfway through the key space, it's not saving you any time. Even if you're able to, test trillions or hundreds of trillions of keys per second, it's still going to be in like the trillion year category. So it's such a huge key space. You just can't brute force check everything. But when we do it with the side channel power analysis, we no longer have to do that brute force because we're not checking the whole key space. We're just attacking one section of it at a time. So we're going to attack this, get the right answer. Then we'll attack this, get the right answer. Then we'll attack this. Oops. Sort of went off the rails there with the boxes, but you get the idea. We're attacking one byte at a time and just doing that 16 times. And checking one byte is just 256 guesses. And this is really per point. You might have 1,000 measurement points. So you might say, I don't know exactly where the AES was happening. So I have a bunch of different things to guess. But even doing that 16 times, it's still a tiny number. So maybe you add some zeros because you had, for example, with 1,000 points, but it's much, much smaller. I mean, even a desktop computer can do this type of search, in seconds or less type thing. So it's this huge improvement in processing or in how many keys you have to search through, how much data you have to search. And that's the real power of these side channel power analysis attacks. So where can you actually apply them? It's important to remember that you can't apply them to just any encryption device ever. So the device has to be performing encryption operation with a unknown but secret key. So the key is, either programmed or loaded into the device right now. And ideally, we can send it encryption request. This just speeds stuff up. So we can say, decrypt this file for us, or I'm going to do a challenge response or something like that. Now, worst case, we just have to watch it while it's doing encryptions that it would do anyway. But ideally, we can request it to perform some operation. So what that looks like is something like an encrypted bootloader. So it might be, a company loads this chip on a board, and to allow people in the field to upgrade it, they have a bootloader where you can send it serial data, and this is the updated software, but it's encrypted. So that way someone can't look at the software and look for errors or vulnerabilities. The device itself has the encryption key inside it, and it uses that to decrypt the file and then program itself. Now, an encrypted bootloader, that gives us everything. We can send it data, it'll decrypt it. It has the key programmed in, so it meets all of these requirements here. Another example is something like a access control card often has challenge response. So to validate that the card is the correct card, you can send it, a request to please encrypt this, and I'll also encrypt the same data, and we'll compare and make sure that we have the same shared secret. So that type of card may be vulnerable to side channel power analysis. So it's worth pointing out two things like credit cards, which are also smart cards. They've put a lot of money into making sure this leakage is as small as possible. So looking back at, this Hamming weight leakage, for example, one thing you could do is you could simply have complementary lines that always switch in the opposite direction. So if I draw in blue here, I could have the same pre-charge, but I could always have a line that's doing the opposite of whatever this one line's doing. So what this means is we always have a consistent number of lines switching. So in total, there's always 4 lines going high, and there's always 4 lines going low. So that reduces our ability to sort of measure these effects. Obviously, in real life, there could be variances in this, so there still could be vulnerabilities, but there's a whole series of countermeasures you can do to reduce the ability of an attacker to use these devices. Where you just can't apply it fundamentally is when the device is not operating. So if you have a hard drive sitting on the table, it's not actively encrypting or decrypting anything. So if that hard drive is encrypted, you can't do a side channel analysis attack against it, because what you need is the hard drive to be plugged in to your computer, for example, or maybe it has a hardware encryption engine in it, computer, and you need it to be actively exchanging data back and forth. And because that data would then be being encrypted and decrypted, you could then apply this attack. Now, the other thing is you need the device to be working with the encryption key, the correct encryption key. So just because you take an encrypted hard drive and plug it in, you can't suddenly apply this attack. The encryption key isn't stored in the hard drive, and so this attack fundamentally can't be used in that situation. If you could capture some of these power measurements while a user was using it, you may then be able to apply this attack to figure out what the encryption key was. And there's quite a few real-life attacks that have been published. So this is actually showing attacks against hardware devices. So that's devices doing encryption and decryption as with hardware peripherals. So, we have an Atmel X Mega, which is a microcontroller. It actually has an AES hardware peripheral that someone has shown how to attack. And there's a whole, quite a range of different types of devices and types of attacks that have been done. So it is a very realistic attack, and it's not just the hardware, the software crypto libraries that are vulnerable. It could be hardware as well. So how do you get started? Fundamentally, what you need is a measuring instrument like an oscilloscope, a device to attack, and just some communications. So this is a really simple getting started, and these, by the way, are linked from as part of the side channel, the Chip Whisperer project. So Chip Whisperer, there's a whole bunch of these tutorials showing you how to get started with the Chip Whisperer software. Now, you need a scope with good USB support. So the Pico scopes are really good for this. They're probably the best USB scopes you can get. You can also use a regular scope that has fast data download, or Ethernet or something like that would work too. Some of the off-brand or lower cost scopes don't actually tend to work so well on the data download, so you should be really careful of that. We need a target, so this is an Atmel AT Mega 328P, so it's like an Arduino-ish device, and we're just loading encryption on it. And finally, we have a serial COM here. So you can sort of source this and build your own. The other thing we have is we've developed the Chip Whisperer Lite. So this board, it varies a little in price. Currently, it's about $250, but that may go up in the second run. So we'll say $250 to $300. And this integrates everything in the previous photograph onto one board. It's also custom designed, so there's some special... The analog front end here is designed to measure very small signal, which a regular scope often is not designed to work with as well. We have a target device, so this is an X Mega target. You can break these away, so if you want to attack a real device, you can separate half the board and attach to your own target. So if you say, hey, I have some piece of hardware I want to test, it's more than possible to do that. So the full training actually uses this board entirely to take you through a whole bunch of hands-on labs. Training is listed on chipwhisperer.io, so there's various online training. But we have part of the open source project is all of this open source documentation. And so this takes you through, how you set up stuff, how you do various attacks, how you manually do one of these CPA attacks. So we've tried to put a lot of resources that will help you learn on your own if you're really interested in doing that. So for example, even setting up setting up this scope, so how you would build this type of board and set it up yourself. So there's a whole lot of resources online if you're interested in getting started in side channel power analysis. But we've tried to put a lot of effort into making the Chip Whisperer Lite a much easier system of getting going. And it's fully open source, so this software we're using is open source. The hardware in the previous photo is open source. So it's designed as a benefit to people really interested in this. So let me finally show you what an attack looks like, and you'll get to see just how easy it is to do this. So I have my Chip Whisperer Lite device, and what's going to happen is it's going to download some configuration to it, and then it's just running a AES encryption algorithm. And I can run, if I say, okay, capture a waveform, it's just going to load a new key, a new piece of plaintext, the same key, and encrypt it. And it'll measure the power, so in the background we can see the power measurement being recorded as well. Now it might not look like a whole lot, but what we're going to do is we could say, record 50 traces. And I'll just capture a bunch of traces like that. And you can see it's very quick to just send a bunch of encryption operations and record them. And we'll just say test live 2. And that's just recorded the data. The other half of it is we need the analyzer. So again, we have this fully open source tool chain that can do this type of analysis. Oops. project. It looks a little crazy because there's some issues with high DPA on this VM that we're using here. But anyway, so what this has done, this has loaded that same data. So you can see this is like the power measurements while it's doing different things. So you can actually, using the power measurements, you can sometimes see a bit, oh, it's going through loops. It's repeating the same stuff here. But anyway, I'm going to enable the attack. And what it's going to do is it's going to rank the most likely encryption byte is ranked at the top. So this is the highest correlation value. The correct ones, because I know they're correct, are marked in red, and I've just told it, these are the correct bytes. So with any luck, you'll see some of the correct bytes filter to the top, and I think the table, unfortunately, the table didn't update there. So let's just run that again. I don't know why that is. But you can see, in fact, the correct bytes are at the top, so it fully recovered the complete encryption key. Again, I think there's an issue with the VM we're using when it's trying to record this. But what's cool is that, I had said, okay, it's recovered the complete key. It not only is going to tell you the key, you can figure out where that was operating. So, oops, I want output versus point. So what this is showing is the location of high correlation over time. So in red is the correct key byte, and we can see these huge peaks. These are really high correlation peaks. And what I can actually do is I can turn on, like this is byte 6. If I say, okay, well, where does byte 7 have a high correlation? And you can see it's just shifted down a bit. And this is because it's just going through a for loop and literally, loading the next byte through that S box. So using this output, I can actually understand a little bit about how that software was working. So side channel power analysis attacks, as I said, not only can break the system, but can tell you a little bit about how it works. All right, so that's the complete introduction to a side channel power analysis attacks, how they are applied and how they work at a very fundamental level. It's important to remember that digital devices fundamentally leak information about the data being manipulated. So it's not a case of an incorrect implementation. It's very fundamental in the design of the digital hardware it's running on. This leakage can then be used as an attack to determine secret data. And this attack relies on the device to be actively manipulating the secret data. So that's the one critical thing, is that we have to be actively using that secret data. It's not enough that it's just sitting there. We're not breaking the encryption still. We're just breaking part of how the implementation was done. It also doesn't require a lot of equipment to get started. So as I showed, there's these, I have these open source tools that you can use. You can even build your own stuff and integrate it with the software. I mean, the integration's done already. You just have to go through the tutorials. So there's really no reason to avoid learning more about side channel power analysis. If you like this training, we're going to be releasing and should have available shortly a whole online course related to side channel power analysis and how you perform it with the Chip Whisperer, as well as covering glitching and other really interesting topics. It uses all of this low-cost hardware, so you can follow along. The whole point of this, it's online, but it's really hands-on. You've got to have the hardware and set stuff up, but it takes you through the complete environment of performing a side channel analysis attack. There is lots of free and open source resources that we publish as part of our Chip Whisperer project, so you can see them all in the documentation there. And finally, if you have sort of some getting started questions, you can always give us a message on the forum, and we're really happy to hear from if people are having successes or questions or what they're up to. So thanks for watching this introduction to side channel power analysis.